Now, remember from last year that we could solve this using a matrix method, and we'll get to that in chapter 7, but for now we're just dealing with it in terms of the function itself. What I'm going to do is recognise that from equation number 2, I get x is equal to 2z minus 12, and in equation number 3, in equation number 3, I get y is equal to 19 minus 3z, 2, and that helps me because I can use that in equation number 1. So in this case, the second and third equations already had an eliminated variable, so I was able to get both x and y in terms of z. It's not nice, but it will work. So in number 1, I get 2 times 2z minus 12 minus 19 minus 3z over 2 plus z is equal to 12. And solving this, I get 4z minus 24 minus 19 over 2 plus 3 over 2z plus z is equal to 12. Moving all the numbers to one side and keeping all the z's on the other side, 4z plus 3 over 2z plus z is 6.5z. So I'll make that 13 over 2z. And 12 plus 24 is 36, plus 19 over 2, 45.5. 45.5. Multiplied by 2, and I get 13z is equal to 91. Z is equal to 91 over 13, and 91 over 13 is 7. Cool. So z is 7, and therefore x is equal to 14 minus 12, which equals 2, and y is equal to 19 minus 21 over 2, which is equal to negative 1, and they're my 3 solutions. Now I've used equation number 1 to determine z, but then equation number 2 to determine x and 3 to determine y. If I put those 3 values back into equation 1, the original equation 1, that's my verification. Go back to the original equation I used to find the first variable. 2 times 2 is 4, minus y, which is negative 1, makes 5, plus 7 makes 12, so it works, and therefore my solution is verified. Any questions? Here's something for you. This is, I couldn't draw this, so I have dragged it straight out of your textbook. It's in there, you can use it. This is their representation of the situation we've just solved. So the situation that we've just solved is 3 planes. Now go back up to it and have a look. These 3 original equations here are in terms of r dot n equals k. There's my k, they're plane equations. So we are solving for 3 planes. If I go down here, got one single star, that means that the 3 planes, none of them were parallel to each other. We get 1 point where they all meet. If, on the other hand, you might have 3 planes that connect in a line, you might get an answer that's a line. You might get 3 planes that are all parallel, which means you won't get an answer at all. You might get 2 parallel and 1 that's not, but then you won't get an answer for all 3 planes. Or you might get all 3 planes, but they don't actually meet anywhere at the same time. So basically, they're all parallel in one axis. See how they're not bent in the axes out of the page? If one of them bent a little bit, they would meet, but they don't. And just remember this. Remember from vectors and planes that n1x plus n2y plus n3z equals k represents plane. That's what we're dealing with. If you do a system of 3 linear equations with 3 unknowns, you're dealing with planes. Just like when you first learned simultaneous equations in year 9, you solved them using substitution or elimination, and then you would graph it on Desmos and find the point of intersection. Now we're graphing planes and finding the point of intersection. But there's a whole bunch of different variations. That's what we've got to deal with. So here are the options. And you remember I mentioned this before. In Sol, with 3 equations, you may have no solution, 1 solution, an infinite number of solutions where that is a line of solutions, or an infinite number of solutions where that's a plane. For there to be a plane of solutions, the 3 planes you have to all be the same plane. That way they all meet on the same plane. For there to be a single line of solutions, you've seen you rotate them around like this top one here, diagram 1. Diagram 2 gives you a line of solutions. And then for diagram 1, diagram 3, 4 and 5 give you no solutions.